Thanks for tuning in, everyone. I'm going to give a talk called the Billion Event Challenge. I'm Chris Bellew. I work at VGW in Perth. I'm a squad lead on the payments team. So in the payments team, we deal with events on a day-to-day basis because we use event sourcing. So it's kind of a personal interest of mine to see how fast we can process a large volume of events. We're not quite a billion events yet, but we're rapidly getting there. So this is a really interesting topic to me. First, I'd just like to say thanks to our sponsors. They've made this event affordable for everyone, so thank you very much for that. So the structure of this talk, I'm going to give a short background into events and why actually we need them and why we want to process them so quickly. And then I'm going to spend the rest of the talk going on a journey of optimization. So trying to tweak some technical things to make my processing system as fast as possible. So the background is that often when I hear and see things about event processing systems and architectures, they're implemented as distributed systems in the cloud, often using many sort of commodity machines or EC2 instances or Azure VMs. They're kind of connected together with queues and then have object storage with all the data stored in them, or using some of the paradigms like MapReduce. I'm kind of interested to see what you can do on one machine. I don't think that's covered as much. I think we tend to over-provision the infrastructure that we have for good reason, because we don't want to run out of resources in a production situation, but we're kind of not utilizing what we're paying for in the cloud. So I'm kind of interested what you can get on a single machine. And because my team has an event processing system in production, and our library of events is growing quite rapidly, I want my team to be able to understand a little bit more about the sort of optimization on a single machine. So I do want to give a bit of a background on events. So I've got an example here of, you can imagine a domain object that represents a hotel booking. So the state changes that happen to the hotel booking are happening over a period of time. And so there's some data associated with each of those things that are going on. And you can store those on objects at the time, and they're called events. So there could be an event for when the hotel booking is created, another event when the occupant is added to that booking, and then maybe the schedule's updated and then paid. So they're a full record of what's happened to that domain object over time. It tells the whole history, tends to be ordered by time, and they're quite useful both storing data, but you can use them to communicate as well. So if you have components in your system that need to react to things that are happening in time, you can pass events around. And that's often called an event-driven architecture. We at VGW and in the payments team actually use the events as the single primary source of truth. So there is no other source of truth that is our main source of truth. This is the source of truth. And any other views on our data are derived from these events. So why event sourcing and why events? It's really nice with events that when something happens, you're recording what happened at the time and you're not changing it. You're keeping that record forever. So it's really good for things like auditing if you've got regulatory needs, or if you want to go back to look at the history of something. It's really nice to have that history. If you're not storing things, the history of things, it's not really possible to know what the state of something was back in time. Whereas with events, because you've got the whole history of time, you can kind of time travel back and pretend you hadn't seen a number of recent events in order to see what the state was further back in time. It's really nice as well, what I said earlier about being able to derive views on your events. So I really like the idea of you're storing all the data as it's happening, making sure you're storing everything that's relevant. And then at any point down the line, even in 10 years, you can transform that representation to something else more useful for all kinds of different purposes, optimized for the read patterns that are going to be used to view that data. Time is the primary dimension for events, which is quite nice because that kind of acts as a queue if you want to process them. So if you've got a number of events recorded in time for a domain object and you want to build up some representation of that domain object, you can look at the events one by one in time, building up state. That state can be overwritten by future events, but then you're overriding it and you're accumulating the state up to now. some examples of remodels. So with that hotel booking example, you can imagine you've got, say, 1,000 bookings for a hotel, and there might be a need to show in an online portal the customer their bookings. So you might have some kind of process which is transforming the events from a customer into a list of bookings for that customer, and that's presented in the portal for that customer. So that's a read model over those events. That you could also have for the housekeeping staff of the hotel, a daily schedule that's being computed from these events. And then maybe less frequently an accounting report that's also based off the same data. And then maybe some 10 years down the line, you have some completely different need for some read model or representation. But because you've got all those events, you've got the flexibility to come up with that. So each of these read models are taking a subset of the information off these events, but they're all basically targeting this same source of truth. The system that's actually creating these read models is often called a populator, and it might look like this in a kind of simple view. You've got events, and then there's a populator that's reading those events. It's doing some transformation of them into a read model and then saving them. And it's basically doing that in a real-time situation. We'll be doing that over and over again in an incremental fashion. So I quite like this, and we have lots of these at work. They're quite easy to understand because they often are doing a very small piece of work inside them. Quite nice and easy to maintain. Even though we've got many of these, I don't really feel like we're sitting on a lot of complexity with each of these because they're kind of small, simple units. The ones we have at work and the kind of structures illustrated here is sequential. It's dealing with things one at a time, which is nice for things to be easy to understand, but it's kind of self-throttling itself. It's blocking its own operation by waiting to produce future read models until the current one's been produced. So it isn't the fastest. I'm well aware there's probably a way faster way to do this, and that's kind of what I'm interested in now. In particular, this is good for a real-time situation. If you've got events coming in a real time at a real-time velocity, you need a certain amount of processing. But there's the other situation where, let's say you've got your event store and you've got some populators that are say caught up and processing data in real time, and then you come up with a new read model. You decide you have a new business need. You have to start that from zero. You have to start that from the earliest part of the queue, because it's going to generate read models for all of those events. So you have to start it off, and it will take time. It's sequential. It will take time to catch up. And at work, we haven't got a billion events yet, but we're getting there, and it takes a few hours to catch up with our solution. So it does kind of slow us down when we're doing releases. We like to think of ourselves as a high-performing team. We do sort of 5, 10, 15 releases a day amongst the 10 engineers. And so we really don't have much scope for waiting a few hours when we're doing a release. But that does happen, and we do a new remodel sort of every week. So it'd be really nice if we could speed that up, get that a lot lower than a few hours. This is the key reason I'm doing this challenge. All right, so given some background of events, I want to go on to the challenge. So as I said before, I want to be able to process 1 billion events as fast as possible on a single machine. The challenge is I'm going to primarily measure the time taken to load all those events from where they're stored, transform them into read models. In this case, I'm going to have one read model for every 10 events. 10 events you could think of representing one hotel booking, for example, and so producing one read model, and then saving those 100 million read models somewhere. And so that's the start and end point that I'm timing here, and I'm going to optimize throughout this challenge. I'm not really focusing on architecting this to be a real-time solution in production that's sort of highly available and reliable. I'm really caring about how fast I can get a catch-up situation, because you could imagine creating a system as part of this challenge that is used as a once-off when a new remodel populator is deployed, that has the job of doing the catch-up, and then some other system that takes over for the real-time, potentially. Some things I'm going to experiment with. The language that I'm implementing this system in, the runtime, the format, both serialization and compression that I'm going to represent these events in, and then the read models that I produce. And then really most of it's going to be how I parallelize this work. So my first solution, I started with something which you use at work every day, which is node.js, so TypeScript. I'm well aware it's probably not the fastest thing to use, but that's okay because we use it because Lots of people know the language. It's very familiar. It's quite easy to get started. So it's kind of the thing we reach for first. So I kind of chose a Node.js application. I generated a billion sort of fictitious events and saved them into a JSON file, because that's also kind of a nice, well understood and used format. And then, yeah, I wrote some code to process them. So I had one huge JSON file of events, and then I was creating one huge JSON file of read models. Except I wasn't, because 1 billion events is 100 gigabytes of JSON, which is a lot. And it turns out Node.js, that's too much for Node.js to deal with in one go. It has a single file limit when you're reading a file of 2 gigabytes. And once you load that file, which will be a string, and then parsing that into JSON, it has a limit of 1 gigabyte each time. So next thing I did was to split that into a number of files. In this case, 1,000. So each one was about 100 megabyte. So 1,000 files in, 1,000 files out. When I was doing that, I had to kind of think very carefully about this, because I want to be able to parallelize these events. And even because I'm splitting them up and doing them in parallel, I need to think about the files that these events are going to end up in. So if you think of an event store that's maybe got 3 bookings in it, booking A, B, and C, they're sort of naturally ordered by time in an event store usually. So in one file, they're kind of all in that one file, even though they're interspersed with each other over time. But if I'm splitting this file up, it's going to be really hard to create a read model for, say, booking A, if half of the events for booking A are in one file and half are in another. So I kind of, I guess, cheated maybe and did a pre-step where I group all of the events for each booking into one file. So I know if I pick up one file, the bookings that I see in there are going to be entirely encapsulated. So that's a step that I did, which should make parallelizing easier as well. So this was the timing of my first solution. So it was actually doing 1,000 iterations of what you're seeing here. So reading events, deserializing them, transforming them into read models, then serializing and writing the result. But I've kind of aggregated the timing here so you can see the breakdown of where it spent most of the timing. And quite clearly you can see of the 26 minutes in total, 19 minutes of that was deserializing. So reading wasn't actually a lot. I was expecting reading and writing, sort of interacting with disk, to take a lot of time, relatively speaking, but it turns out that JSON is a fairly verbose way to encode data, and it's fairly sort of CPU intensive to actually interpret that. And it looks like the Node.js implementation of that, I don't really have a barometer yet as to whether it's fast or not, but it certainly looks like it's taking a lot of time. So that's the first solution. So at least I have kind of a yardstick for what maybe a slow performance will look like, because I think all the other ideas I'm going to try are only going to make it faster. So we're starting from a position of 26 minutes. These are the ideas I have for optimizing. So I've started with JSON and Node.js. I want to try something that's not Node.js. I also want to try something that's not JSON. I think that's probably not the most compact way to represent this data. Maybe want to try some compression algorithms, and also want to try and make it parallelized, so not sequential. So let's focus on not Node.js. So what other choices do I have? Obviously I have innumerable choices, but I've kind of picked 4 that I've heard on the grapevine that are fast. So Java, C++, Go, and Rust. So for me, I happen to have spent more time in Rust than any of the others. It's something that a language that I find particularly interesting. So I'm going to arbitrarily pick this as the one I'm going to try to be faster. I have heard it's a modern language and it should be fast, so it should actually be quite hopeful. It is a statically typed language, which is an improvement hopefully on Node.js or JavaScript, which is a dynamically typed language. So the compiler is able to know a lot more about what's going on with the data that it's representing, so it can make a lot more optimizations. It isn't the only statically typed language in this list, but that should be an advantage compared to JavaScript. It is natively compiled, so it's compiled ahead of time, so a lot of optimizations can be made at the compilation step as opposed to at runtime. So that's kind of nice. There's no pausing where it's doing just-in-time compilation. It's all done ahead of time. And one of the really unique things about Rust is its memory model. So it uses a model called the ownership model, where each variable you have in your code or each piece of data you have has a very clear owner. And it can be one of the reasons Rust is quite difficult to learn, because you have to be really clear to the compiler who owns a piece of data. And when you're sort of passing it around between functions or between threads, the compiler really wants you to be clear about who's going to be owning that data. So it can make it difficult to learn, but the end result is that the compiler has a lot more information about how that data can change, so it's able to make even more optimizations, which is really, I think, one of the reasons why this should be faster. So this was my implementation in Rust compared to Node.js. So total time more than twice as fast, so 9 minutes, 9.5 minutes overall. Looks like the bulk of that time is much faster deserialization process. So the reading and writing was similar. You'd expect it's JSON. It's using the same disk. The transforming was also faster. I guess that you might expect that too. So that's a good move. So Rust is, I think, what I'm going to stick with for the rest of this. I don't really want to jump around languages at this point. I think there are other optimizations to make that are probably easier. So let's try not representing it as JSON. And again, I have innumerable choices here, and I've picked 3 that I've heard are fast based upon benchmarks from the internet. They're all binary representation as opposed to the string JSON representation, which I think will make it more compact. Bin code and archive. I've been calling it RKYV for a year. My friend recently told me it's probably pronounced archive, and I think they're probably right. They're both Rust. They appear to be only Rust-based serialization formats. Message pack is a bit more commonplace. So I'm going to try those 3. And I'm measuring them both upon the size that they're represented as, but also the time it takes to do the steps in the process that are relevant to the serialization format. So the reading, you might imagine, would be faster or slower based upon the size of the file that it's reading. Same with the writing, and then deserializing and serializing, you expect that to change in time as well. So the size of all of the alternative choices were a lot smaller than JSON, but the smaller ones did actually appear to be slower compared to each other, but not compared to JSON. So although bin code was sort of a quarter of the size on disk, it was a lot faster than JSON in terms of its deserialization and serializing, but it wasn't quite as fast as archive and message pack, which managed to be faster, although not represent the data quite as compactly. So I think because I'm optimizing for ultimate end-to-end time here, I should really choose the one that gives me the shortest time, and that's archive. So that's the one I'm going to go through. So compression, what have I got choices there? So again, I've chosen a small set. Deflate, which is commonly used in zip files and gzip. Snappy, which is a more modern compression algorithm. And then there's LZ4 as well. These are, again, ones that I just picked that in theory should be fairly fast. But rather than thinking in theory, again, let's measure. So compared to archive with no compression, we've got the other ones here. So quite impressively, Deflate got down to 6 gigabytes, which is pretty impressive. Snappy and LZ4, again, quite a lot smaller than without any compression, but they have introduced a lot of decompression and compression time, especially Deflate. Deflate just needed a long time to compress. I'm not sure why. I mean, it's probably one of the older compression algorithms, but it is still very effective at compressing. So it just takes a lot of time to do it. But actually none of them, if you measure the end-to-end time, the compression that they made in terms of making the file smaller wasn't able to make up for the fact that they added more extra time in the absolute processing of this. So I'm actually just not going to use any compression. The numbers are telling me that maybe I shouldn't. So I'm just going to stick with archive with no compression. And this is the one that's really interesting to me, parallelizing resources. So what actually can be parallelized? I think that the most obvious one is CPU work, because CPUs tend to have lots of cores on them. So you can have many threads in your program that are making use of CPU cores. And I think the main parts of the program that are going to benefit from that are the deserialization, and then the transformation into read models, and then serialization at the end. I wonder whether parallelizing disk access is also going to help. I actually have no idea. Maybe reading and writing 2 files is faster than one. If you do it in parallel, I'm not sure. So that's something that I'm definitely going to measure. So I'm going to start off, I am going to parallelize, but I'm just going to start with 3 threads. So I'm going to have one thread that's doing all the reading. It's just going to be reading the files as fast as possible. It's going to put the files on a queue. And then there's going to be a processing thread, which is going to be receiving those, processing them as fast as possible. And then another thread for writing the results as fast as possible. So I've tried to keep that simple to start with. I'm going to do this on my machine. So my machine at home, which is a Intel Core i9. So it's got 10 cores, 20 if you include hyperthreading, although sort of strictly it's only 10. But because of that sort of 10, 20 core hybrid there, I'm interested to know how many threads is appropriate to sort of make use of those cores, whether you should only really use 10, should you use 20, or should you use somewhere in between. Then I've got 32 gig of RAM, which I think should be enough. And then the disk I'm using is a relatively modern SSD, and I'm interested to know whether there's any parallelization I can have around the access to that. So what I've got here is a visualization. I've done some measurements while the program was running. I've saved the results, and I've made a visualization here, which represents what each thread is doing. So I've got 3 threads. I've got my read thread. It's doing a bunch of work for about half the time. So I'm not sure if you can really see, but it should be clearer in future visualizations. But in this one, those slivers there are individual partitions getting processed. Then you've got the processing thread, which is solid color the whole way, which essentially means it's busy the whole time. And then the write thread, which is a little bit spotty, so I don't think that's fully busy the whole time. So the read thread's got this big gap here, which is telling me that for half the time it is busy reading, and then once it's finished reading, it's got no more work to do. It's done all its job, and it's got to wait for the processing and the writing to happen before it's done. So it's 2 minutes 14 seconds, which is kind of comparable to what I had before when I had no parallelization. So it's not really too much sticking out there. But I'm thinking what I should do is add more processing threads, because it looks like that's the bottleneck. So what if I go up to that core count, a total of 10, if I add 8 processing threads and then keep my 1 reading and 1 writing thread? So with the same visualization, this is what I'm getting. So you can see the processing threads here. They're a lot more patchy. So there are smatterings of color where they're each doing work, but they're not sort of fully utilized. There's definitely patches where it's not doing anything. And the total time has dropped quite a lot. So we're down to 44 seconds. So we've taken a huge chunk off just by parallelizing some of that processing. And it looks like the processing is sped up enough that the read thread is now the bottleneck. I think the read thread is more solid color than the write thread, if you look at it that way. So I think what I'll do is I'll add another read thread, see if that actually helps. So let's go 2 instead of 1. Interestingly, the time did drop a little bit, so I think that did help. The read threads still look quite busy though, but the processing threads, I did drop 1 processing thread to keep the total at 10, but it does look like they're much more better utilized now. So I think that was good in terms of feeding those processing threads a little better. So I might actually try and add another read thread and see what happens, see if I can keep getting incremental benefits. So up to 3 read threads now. Interestingly, the 2 of those read threads appear to be busy, but that third one isn't quite as busy at the end there. So I wonder if maybe it's starting to sort of go as fast as it can from that disk, and that third thread isn't having much effect when it's saturated. The 6 processing threads do appear to be a lot more utilized now. They don't appear to be entirely the blocking factor though, because there is a little bit of underutilization at the end there. So the write thread appears to be a lot more busy, and we've lost another 2 seconds. So we're down to 36 seconds, which from the original 9 minutes is going pretty well. So I think what I might do is bump up the processing threads and see if that sort of solid utilization there is actually holding it back in any way. So jump up to 12, so that actually did help. So we're over the sort of natural core count of the CPU now. So I think there is some benefit to that hyperthreading, that beyond that natural core count, the hyperthreading is able to do some more. And it appears those 12 threads I've got now doing the processing are not fully utilized. The 3 read threads appear to be the bottleneck again. So I think probably I might go and add another read thread and see what happens. Didn't do a lot, So we might be reaching diminishing returns on that. Now, it looks like those read threads are busy, but what that's actually telling us with those solid colors is the units of work where it's doing reading are taking the full amount of time that's sort of saturating those threads, but it doesn't necessarily mean the disk, or it's waiting for if the disk is fully utilized and feeding all of those threads at the most it can. There may actually be time in that sort of coloring that is where the disk is kind of fully saturated, not able to feed those threads, and they're just waiting. The threads are waiting for disk. So I wonder if that might be the end, or should I do another read thread? Let's see what happens. Cool, 5 read threads. I think we've maxed it out now. So we're at 32 seconds on my machine. I don't think adding more processing threads will help. I don't think adding another read thread will help. Write thread will help. I think it's maybe saturated on that. So why did adding more read threads help performance? That seemed to be one of the main things that was helping me here. One of the things is I'm using an SSD, and the big thing about SSDs is they've got many flash chips on them. So different to how a sort of traditional spinning hard drive would work, they're able to actually do reads and writes in parallel, because if you've got a file on one chip on the SSD, that may be being read, but you can get another file on a different chip, as long as the bus between the CPU and the disk is able to support that. So I think that may be what's happening here. I'm loading multiple files off the disk in parallel, and they're maybe stored on different chips on the flash drive. So I'm able to get sort of really high performance by loading multiple. The NVMe interface spec, which my SSD card supports, some confirmation on a website on the internet here is that, yeah, if you're able to access multiple files in parallel, if they're running on a distinct core, you can actually take advantage of that and do reading and writing in parallel with NVMe. So I've done some parallelization. What can I do to improve it? I could go out and get some faster disks. The disk I was running it on was relatively modern. I only bought it a few months ago when my previous one ran out of space. So I'm not sure that's going to be something I'm going to be able to do very easily and get a huge amount of benefit. I could get more disks though. I could get more cores, maybe go and buy one of the new CPUs that's got more cores. Faster clock speed maybe on each individual core, but I think we've maybe Moore's law has slowed down in that regard, so I don't know if that's going to be something I'm going to be able to do. So I did actually have a previous disk before that one filled up and I bought my new one. I had another SSD, so what I'm going to try is plug that one back in and try and distribute the data across both of those and see if I can get a speed up. So I'm just going to start with two threads reading and writing, one for each disk, and then say 16 threads processing. And the same visualization, so I did get a bit of a speed up there. So I dropped 6 seconds, and you can see the two read threads, and you can see they're quite different. One of them appears to be busy the whole time, and the other one appears to be busy for only or sort of 80% of the time. And I think that's probably because one of them is a lot faster because it's a lot newer. So one of them's able to read all the files it's responsible for pretty quickly, and the other one's lagging behind there. So that may be a bit of a problem. I'm not able to sort of get too much benefit because one's kind of just slower and needs more time. The processing threads aren't that busy and the write thread isn't. So that's, I could try more read threads because I did get a speed up when I did that on one SSD. So let's see what happens with that. And yeah, I got a speed up. So 3 seconds less time. Again, you can see which two threads are for the faster SSD. And the processing threads, write threads, not heavily utilized. So I think I might try it again, giving more read threads, go up to 8 instead of 4. Dropped at 1 second. So diminishing returns appears to be about 4 threads per SSD. Interestingly, the write threads there are starting to get a bit busy. So maybe I could bump those write threads up and see if I get the same boost like I did with the read threads. Yeah, it didn't really. Maybe I could do that more, but it appears as though it's not really taking too much time there beyond what the read threads and processing threads are doing. So I might be reaching diminishing returns with the 2 disks. So that probably is the most I can get to, 34 seconds on my home machine. So what do? I could go out and buy more disks. That appears to be the magic. The CPU, I don't appear to be fully utilizing that. So I could go to PLE and get sort of 4 more drives. Or I could call up Jeff Bezos and say, hey, one of your machines, can I borrow one of those? One of those big beefy ones. And he said, yeah, I'm going to be in space. I don't need these. You can have these. So yeah, go for your life. So I looked up the instances and I found this quite beefy one here that's got 96 vCPUs, quite a lot of RAM, but it has got 4 quite beefy NVMe SSDs. So I'm hoping that that's going to be a reason why I might get some faster performance on this particular machine. So I'll mount those 4 SSDs. Again, I'll start with 1 thread reading from each, and maybe just the 2 threads writing, and maybe 22 threads processing. Let's see what we get from that. So that was quite nice. Got another fairly substantial performance bump, 11 seconds down, so down to 23 seconds now. The 4 read threads, yep, appear to be the bottleneck to start off with before. So that's interesting. I am starting to see something happen on the left-hand side of the chart. So that is actually the serializing step, that big orange chunk. So I'm not entirely sure why, but it's an interesting observation that at the start of the process, those threads appear to be having problems sort of deserializing before they're able to sort of settle down. So I'm not entirely sure what's happening there, but that's maybe some future investigation. Again, when I was on my local machine, it helped bumping up the read threads, so I'm going to do that here. Cool, that helped. So 8 read threads helped, dropped another 4 seconds, so 19 seconds, still getting some improvements here. The 22 processing threads appear to be a good number, like fairly well utilized, but don't appear to be the bottleneck. So I think, again, I might bump up the read threads and see if I can get 4 per SSD. And that had quite a big impact and actually made things slower. So those read threads are kind of busy. Processing threads are kind of busy, but the write threads, they look like now they're kind of taking time beyond the others, and they weren't before. So that might actually be our bottleneck now. So I'm going to bump up the write threads. All right, and we're back to a situation where everything's taking sort of approximately the same amount of time, and we've dropped another 9 seconds. So we're down to 18 seconds, which is pretty cool. So that might be it. I think that's all I can do with the ideas that I had. So I do really want to get it sub 10 seconds. Does anyone have any ideas what I should try? I maybe try some more larger EC2 instances. There are ones that are expensive. The one I used was about $3 an hour, but there's one that's $32 an hour. There's one that's $109 an hour. The first one's got more SSDs, which, yeah, I think that'll help. The second one, interestingly, doesn't have any local storage, but it does have quite a lot of network associated with it. I think this one's got 4 times 100 gigabit network. So maybe that's when I could start using some of the storage services in AWS like S3 or EBS, because I understand that you can actually get quite a lot of throughput out of those when you have them at scale. So that might be an interesting thing to try. And then I didn't really say that there were any rules about having to have disks. So I could just stick all the events in memory in a RAM disk and process those. I imagine that would be a fairly good thing to do for performance. And then the other thing I did when I parallelized is I didn't revisit compression. I was assessing that when it was sequential. So maybe there may be a performance boost if I do compression in parallel as well. So what did I learn? I basically learned what fast looks like, I think. I mean, it's taking hours in some of our systems in production, which is fine for what we need. But by running things only on a single machine, I was able to drop it down to sort of 9 minutes, and then a few minutes, and all the way down to 17 seconds on a single machine, albeit a fairly beefy one in AWS. So the main thing that I did was had a more compact format for representing the data. I was parallelizing my use of the SSDs, and then the processing part, I was parallelizing on the CPU as well. So, yep, I think that I also learned that 1 billion events is a lot of JSON. So 100 gigabytes of JSON is a lot. I imagine almost anything apart from XML will be more compact than JSON. So it's nice that it's machine readable and it's very compatible with a lot of things, but it's probably not something you should use if you want a high performance system. Compression reduces size, but in my case, it actually added to the total time because the time taken to decompress and compress was prohibitive in terms of improving the performance. So that was a kind of unexpected thing. I thought compression would help the reading and writing so much that overall it would have a performance benefit. Yeah, I found that utilizing an SSD in parallel was possible by using loading files on multiple threads. So that was an unexpected outcome for me. And when I tried my two SSDs, one of them wasn't as fast as the other. And I think that really kind of, yeah, that was one of the reasons why I didn't get so much when I had two SSDs running so much of an improvement. And definitely measure everything, because I had some surprises in here. My theory wasn't always what I got in practice. So tying it back to the original solution, down to 18 seconds is, in theory, the fastest we could get our system with an approach like this. Is that faster than the sort of distributed cloud solutions you hear about? I'm not sure, because this probably would reach a point where you couldn't scale it too much more. I was already reaching diminishing returns, whereas in a cloud distributed solution, it could scale much more. So ultimately, I think a distributed solution could get faster, but would the complexity be worth it? This app was kind of simple. I didn't really need much infrastructure even when I put it in the cloud. But on the other hand, I did kind of do that pre-processing step, which, even though I was running this as a kind of once-off batch job, made this a bit more complex. And then if I wanted to make this a real-time system, that would again be more complexity. So I'm not sure if it is more complex or not. I guess it depends what you're optimizing for and what your situation is. So thank you for listening. I'll take any questions and interested in any other ideas or feedback. Thank you.